Wait for the green dot. Yes, there we go. We should be good. Hello and welcome back to differential equations section 4.4. We're still exploring Laplace transforms. This would be derivatives, integrals, and products of transforms. So we know that we can't take derivative of two functions multiplied without the product rule. If we have multiplication of two functions and we have integral of that, we usually use integration by parts. So for Laplace transform, because it is in the base integral, we don't get to just take a look at a product and just take whatever we need to do. So we have to define few of these, define few of the theorems and so on to deal with such cases. So first we're going to define convolution of two functions. Convolution. So the convolution f star, like this, f star g of the piecewise continuous function f and g is defined for all t larger or equal than 0 as follows. So the convolution f and g of t is the integral 0 to t f of tau g of t minus tau d tau. Now this tau as a new variable that we are introducing here, which we can use for shifting and so on. But now the other part of this is to understand that, and now let me just ask a question, why? Well, it's a definition. Now, why would we need this? Why? I'm going to say that the Laplace transform of the convolution is going to be multiplication of individual Laplace transforms. So if you are multiplying two Laplace transforms, you're getting convolution on the other end. So now you define convolution as the integral. You know that Laplace transform is also defined through the integral. And what do we use it for? Well, convolution of f and g, Laplace of the convolution is equal to product of two Laplace. Laplace of f times Laplace of g. Properties of convolution is that the convolution is commutative, because you have, as you can see, so just by looking at this purple line over here, you can immediately conclude, right, that convolution is commutative, because you have a product. Have a product on the right hand side, so it can swap. So let's just compute one of the examples. So what do I have? I have, let's say, cosine t convoluted or convolved with sine t. So by definition, it's 0 to t of cosine tau times sine of t minus tau, d tau. Now, how do you integrate this? Can't really use u sub because they don't have the same argument, right? Exactly. So we can't integrate this because we have two different arguments. But then in pre-calc 2, at one point you were handed some formulas and told not to memorize them because you will never need them. And now you need them. And you don't know them. I know. Such is life. So there are formulas that are called product to sum and sum to product. And they could be derived and figured out. But you were given those formulas because, why memorize at that point? So, now you have to recall the formula that you never learned and use it to transform this integral so you can actually integrate. So I'll just say over here formula. So what is cosine A times sine B equal to? It's 1/2 sine of A plus B minus sine of A minus B. So that's the formula, and we know that A, by comparing this and this, A is tau, and the B is t minus tau. So, let me write that. So, A is equal to tau, and B is equal to t minus tau, and we are going to plug all of that in. So the integral from up there now becomes 0 to t, and we have 1/2 of sine, and then what you have here is A plus B, so you need to add these two, so it's just sine t. And we have a minus sine, and then A minus this is going to be negative t minus 2 tau. And when we have d tau. Right? Oh no, that's A plus 2 tau. That's what I said. Thank you. Good. So now, what I'm going to do is, I could have wrote it as 2 tau minus t. There we go. So now we kick 1/2 in front. We integrate. The integral of sine t is negative cosine t. No, sorry, lied. This is integrated in terms of tau. And this functions in terms of t, so it's just a constant. So I have tau times sine t minus, the integral of sine is negative cosine, so plus cosine 2 tau minus t divided by 2. And all of this computed from 0 to t. So now each tau is going to get a t or a 0. So I have 1/2 t sine t plus 1/2, when you plug in t for tau, you get cosine t. Now we plug in 0. When I plug in 0, the first one dies. The second one becomes plus cosine of 1/2 cosine of negative t. Sorry, minus cosine of negative t. So let me just one more time. So t goes for tau, becomes t sine t. T goes for tau here, that becomes 2t minus t is single t. And at the end, 0 goes here, kills it, and 0 goes here, becomes cosine of negative t, everything divided by 2. Awesome. So now we just simplify this and we're done. It's 1/2 t sine t plus 1/2 cosine t, and then cosine is even function, so this minus just disappears, plus minus 1/2 cosine of t. These guys cancel out, and we have 1/2 t sine t. Now we don't have plus c. Why don't we have plus c? Yes, it's a definite integral 0 to t, right? So we compute it. There's no plus c. So hopefully there will be no plus c on exam on this question for you, and there will be plus c on others when you compute definite integral. Great. So what we've seen is that the convolution of cosine t with sine t is 1/2 t sine t. Next time someone asks you what do you know, tell them that you know the convolution. See if they can even spell it. Yet alone do it. All right. So convolution property, we are looking for theorem 1, convolution property. This is what we have. Laplace transform of f of t convolved with g of t is equal to Laplace transform of f of t times Laplace transform of g of t. And then finally, inverse Laplace transform of f of s times g of s is equal to the convolution between f of t and g of t. Which one is the useful one? Which one is the useful one? And why? Which one is the useful one? Come on, guys. It's obvious. The one on the bottom. The inverse one. What are you going to do with the top one? Nothing, right? The bottom one, when you have to find inverse Laplace, if you have a product of two functions there, right? We know that you might be stuck with partial fraction decomposition if the stuff that you see there is not immediately on the easy to see chart, right, which is provided to you. But what happens if you have two of them multiply each other, right? So you can take a look on their individual Laplace transforms and perform convolution of those. So if you see this procedure that I just did here, it doesn't look like it's related to differential equations because none of this stuff is differential equations work, this particular example. But if your individual Laplace transforms were cosine and sine, you can't just multiply them together. You have to actually go and get convolution of those two answers. So it's the one on the bottom that I'm going to put in additional purple box as the one that you are supposed to consider more, because it's useful for your inverse Laplace. And they actually have a wonderful example in a book to support this. We could do a different one. We can do this one. It doesn't really matter. So so I'll put over here, did the Laplace to get, and now we have 2 over s minus 1 s squared plus 4. Right? So now you are looking at this and you say, this is clearly partial fraction decomposition to do the inverse Laplace to go back into your function, which is solution of differential equation. So now you can do your partial fractions, or you can say, but I can write this as a product of two functions that are easily transformed, and then I convolve those two inverses. So you can write this as 1 over s minus 1 times 2 over s squared plus 4. So I'm able to break these into two basic functions. And now what I know that the inverse Laplace for this one is e to the minus t, and the inverse Laplace for this one is the sine 2t. So we know this inverse Laplace, but these are individual inverse Laplace. And now we convolve these two. I do the convolution of these to actually get the answer. Did this make any sense? Okay, 3 people are shaking their head, 2 are not paying attention, and 1 is not saying anything. So that's out of 700 that are in class right now. So.
So then you just do the whole integration thing?
Yes, we just do the integration thing.
How do you set up the s squared plus 4 for partial fraction? That one?
S squared plus 4, this would be set up as a over s minus 1 plus bx over c s squared plus 4, because you can't factor it. So partial fraction decomposition, sorry, plus in between, there's no doubt that you can solve this with partial fraction decomposition. What the hell's going on over here? So I am able to do the individual inverse Laplace on these pieces. And so now I can say that the inverse Laplace of 2 over s minus 1 s squared plus 4 is equal to, and then what I have here would be the inverse Laplace of 1 over s minus 1 convolved with the inverse Laplace of 2 over s squared plus 4. So I am applying inverse Laplace on each one individually. And then I'm doing convolution of them. So what I'm getting now is that I'm supposed to take e to the negative t and convolve that with sine 2t. And that will give me the answer. Well, that's when I write the convolution, because now you have the two functions f and g, and now you apply the integral, right? Because one is e, one is sine, and so on. So cool, right? So now, what am I going to do? What's better to integrate? Gonna be equally evil, right? If I have that, I'll have to do integration by parts either way, I think. I mean, let's do it. Just do it. So let's see. Oh, but then this is 2t. I can integrate it either way. I'm integrating in terms of tau minus t. Okay. Okay. So when we do the convolution, right, we have, this is going to be the integral 0 to t. Then we change the first one into a tau and the second one into t minus tau. Oh, see, that's not going to be good, because then I have to do the 2t. Okay, so I'm going to switch this and write it as sine 2t convolved with e. It's commutative, right? So this way. So now I will have sine of 2 tau times e to the negative t minus tau d tau. Now I can apply the minus and get integral 0 to t sine 2 tau times e to the negative t plus tau d tau. But then this e to the negative t is a constant, right? So this piece can be written as e to the negative t times e to the tau. So I can kick out e to the negative t in front of the integral. You're not used to this kicking function in front of integral, but you have to understand the integrals in terms of tau. So e to the t is a constant, right? So you can kick that outside, and you keep the rest. sine 2 tau times e to the tau d tau. Something is off. I can't really place. Oh, it's e to the t. 1 over s minus 1 is e to the positive t. That's the thing that it's off. Okay, that's a positive there. That's a positive, that's a negative. And then that's a positive, that's a negative. So this is e to the t, e to the negative tau. Okay. So now we need to integrate this. How do we integrate this? And don't say carefully. It's integration by parts, right? No one cares? No. So e to the t, and then on the side we have u equals e to the negative tau, dv equals sine 2 tau d tau, and then du is negative e negative tau, and v is equal to integral of sine is negative cosine. So I have negative cosine tau, no, negative cosine 2 tau divided by 2. And now we put the formula together. So this is going to be negative e to the tau cosine 2 tau over 2. There we go. Minus and a minus and a minus, the minus still remains. Integral e to the negative tau cosine 2 tau, and still over 2 d tau. And what do you do? One more time, right? So now we do this one more time, integration by parts. And then we move the term, right? It's just some little bit of busy work, nothing major. 1/2 e to the tau cosine of 2 tau minus, and now we still have more of the same, right? This is gonna be now cosine 2 tau d tau, which will give me positive sine 2 tau over 2. So what do I have? I have this, another parenthesis, e to the negative tau times sine 2 tau over 2 minus, and the du minus will give me plus, and I have e to the negative tau times the sine of 2 tau over 2. That's the integral, so you have d tau. So that's the same as the one that you started with, but let's clean it up. E to the t times negative 1/2 e to the tau cosine 2 tau minus 1/2 e negative tau sine 2 tau, and then we have plus, nope, have minus 1/2 e to the negative tau sine 2 tau.
You're supposed to Well, what else would, I think you like basically pulled out the 1/2 so you didn't put it in. When you did like the section or the first. And you just like ignored the 2 underneath it.
You think there is an additional half? When I do the you show where?
You see like e negative tau sine 2 tau over 4.
Why over 4 when the integral up there doesn't have it at all? When I do there's over 2, right? That's the over 2. Oh, there's a 1/2 over here.
Yeah.
Okay. Put the red 1/2, which changes this into a 4. Changes this into a 4.
Why go to that?
This half. I forgot it.
Oh, you pulled that out?
Mm-hmm.
Okay.
I'll send it. He pulled it. So now, well, why are these two terms the same now? 1/4 the sine. Oh, because I didn't integrate. So 1/4 integral e to the tan sine 2 tau. Okay. So now that integral is the same as the integral we started from. This integral and this integral are the same. Can't really see same. So I'm going to take this 1/4 and move it to the other side. To get e to the t 5/4 of integral e to the negative tau sine 2t d tau is equal to e to the t negative 1/2 e to the tau cosine 2 tau minus 1/4 e to the negative tau sine 2 tau. Great. And now so you don't get to make a 0 if you divide by e to the t. Or you move only 4/5 to both sides. Five quarters, so 4/5, so that's gonna be 2/5. So e to the t and then a negative 2/5 e tau cosine 2 tau minus 1/5 e to the negative tau sine 2 tau. And now you apply 0 and t. E to the t. Apply first t. So it's going to be negative 2/5 e to the t cosine 2t minus another t over here, which is 1/5 e to the negative t sine of 2t. And now when you apply 0, 0 is going to die in the sine. It's going to survive in cosine as just negative 2/5, so plus 2/5. There we go. It's good? Yeah, call it good. If you are to do partial fractional composition, you're going to come up with the same thing. So benefit of this is for the inverse Laplace transform, so you can actually bypass, right? Because if you're better with integration, use this. If you're better with the partial fraction, the composition, use of the chart, you do that one, right? So this is the convenience thing.
Seems easier than that.
Well, look, the part of it's personal preference, right? As I said, engineers like Laplace more because you transform differential equation into algebraic equation, you solve algebraic equation for Fs, and you hit it with the inverse Laplace. Mathematica solves it even faster. Right? So I don't see anyone arguing with that one, right? So this is a convenience, if you want to call it convenience, because if you're good with integration, right, then this thing just flies. Now you definitely don't want to do it. I mean, you would never do it. When I finish my complex lectures, I'm going to solve integral like this, right? Integral like this. I'm going to solve it in 3 steps because the complex values make this long calculation, painful calculation, trivial. So if you're looking at it this way, obviously, and you have nested integration by parts, and you have to do it again, and you have to, right? Then in that case, this defeats the purpose. It becomes really long, right? But I mean, let me peek into homework and see if the problems are, because anytime you multiply e by sine, you're going to end up with a loop on the right, the double integration by parts. Let me just peek in homework and see, because if you have, sine times sine or something that you can deal with using formulas, then it becomes much more. Okay, so problem 25 has e to the 2t times, or e to the negative 2t times e to, yeah, so these are not an issue at all. And then God knows if you factor this, what you're going to get here. But they don't sound that awful to begin with. That's the best part. I mean, you write this as a deterrent to someone telling you, yeah, what do you know? Ta-da! What do you know?
Is it Wednesday, 7 o'clock?
Yes. And then Thursday, 7 o'clock. What? No. No, we have to postpone it yet another week.
Really?
Yeah, because that snow messed everything up. That I was supposed to be done, and then I had 2 consecutive Rutgers Wednesdays, right? And then induction on Thursday, which is where I originally moved it. I moved it for a Wednesday, then the thing, I moved it for Thursday, the thing. So following one. It's one lecture, which is where we are going to do this integral in 3 steps, rather than going with all this nested integration by part.
Can I use that in the final?
You got these on the final?
My final, yes. Good luck on others' finals. Okay. Now we have a differentiation of transforms, and we are looking at Laplace of negative t times f of t is equal to f prime of s. And you can do the proofs and things by plugging into the formula. So I'll put or equivalently. The f of t is equal to the inverse Laplace of f of s, which is negative 1 over t inverse Laplace of the derivative. Is this useful? And I would say it's very useful. Because remember that differentiating is easier than integrating, right? So why struggle, suffer, and work with inverse Laplace transform if you can just take a derivative in terms of s and then look at the chart again? So that's another kind of free method to go faster about inverse Laplace. Again, inverse Laplace is the one that is the boss, and the other equation will actually be helpful. So say I have to find the problem. The one that is done in the book you can read. I feel cheap when I pick the example that you can read. So just want to get the example from the exercises. Oh, they're there. Okay. Okay, so any of these is fine. How about t squared cosine 2t? So problem 16 in the textbook, f of t is given as t squared cosine 2t. What happened? I still don't know who watched it.
No, I said the cosine would be weird.
Cosine looks weird. Is that a better cosine according to your standards? Good. So let's say I want to transform this into Laplace. Oof. Because I gotta apply that integral. So I have to have this times e to the negative st, right? dt. And when you integrate it out, it's going to be in terms of s. Right? So applying is just a living nightmare, right? So what can I do instead? Now this is not what it's used for. We'll do the inverse one, but what you can do instead? You have your f of t. You plug it up there. Oh no, this is just a forward forever example to compute for no reason. Let's do the inverse one, the one that makes sense. What you would do here is you have f of t, you plug it here, and then it becomes t cubed, and then you do the Laplace transform for that. That will give you the derivative of the Laplace. Whatever. So let's see if we can find the inverse Laplace, the problem that is actually useful. I don't see any problems for inverse Laplace on this thing. They gave one as the example, they gave two as the example in the text, but they are not asking any exercises on it, which is the thing you need to know. Oh. Okay. I have no clue how to do this one, so let's do that one. 27. Fs is given as ln of 1 plus 1 over s squared. So what's f of t? No coughing. Do we have any inverse Laplace transform things in our chart? Let's check. Laplace transform, images, and we pick up, let's take the busy chart. Busy chart should have a lot. And now we are looking at the right-hand column for ln. If we don't find any of these to have ln, then we don't get to transform it back, right? So you're looking, and I don't see any of these to have ln. And our problem has ln. If you see our problem, so this, the second column, first column is f of t, second column is fs, right? Now look at our f of s. F of s is equal to ln of stuff. So you don't get to use the chart because it's not on the chart. So what we can do is your f of t, which is what you need to find, is negative 1 over t times the Laplace of the derivative of this, which kills ln. So use that f of t is equal to negative 1 over t times the Laplace of f prime of s. So the answer, f of t, that I'm looking for is negative 1 over t times the Laplace transform of, and now I have to come up with the derivative of this. We know the derivative is 1 plus 1 over s squared times the derivative of it, right? And the derivative of it is what? Negative 2 over s cubed. Is that true? Because that's derivative 1 is 0, and the derivative of s to the minus 2 is minus 2 s to the minus 3. Yes, okay. So this is negative 1 over t Laplace of, now multiply by 3s, s cubed, so that's negative 2 divided by s cubed plus s. And you see that now you can actually find that Laplace transform. That's the easy one. So it's a Laplace of negative 2 divided by s times s squared plus 1. Now you can use your partial fraction decomposition, but you can also do convolution. Right? Because you have a product of two of these. So if you take a look again at the chart, you have a negative 2 over s squared plus 1, I believe. So negative 2 over, it's a sign, right? So this could be now further computed as this. You can use Laplace transform of negative 2 over s if you want to, convoluted with Laplace of 1 over s squared plus 1, which is the sign, and that's negative 1 over t. 1 over s is inverse Laplace of 1 over s. Why am I writing Laplace? This is supposed to be inverse Laplace. It's supposed to be inverse Laplace. It's inverse Laplace, inverse Laplace, inverse Laplace, inverse Laplace, because we are already in S domain. I'm just not paying attention. So yes, 1 over s is 1, so the whole thing is just negative 2, right? So we are convolving negative 2 with what? Sine of t. So we couldn't do inverse Laplace at all because ln is not on the chart. Well, there's the integral you can crank. But then this convolution here, right? Cheap and easy. What? Well, it's negative 2, so that's just a constant. No, that's on the outside. Convolution is done separately, so integral for convolution would be applied over here. Yeah. Well, let's write it out since you are asking. So negative 1 over t. Negative 1 over t times the integral 0 to t of negative 2 times sine of t minus tau d tau. Bueno? So this becomes 2 over t integral, well, I don't need the integral now, I can integrate this, so it's negative cosine of t minus tau from 0 to t, and that's 2 over t. Plug in t, it's a cosine of 0, right, which is 1, so it's going to be negative 1, and then plug in 0 for tau, you're going to have plus cosine. Make sense?
Yeah, so the negative 2 is like the actual t part.
Yes, negative 2, that's the first
You
function.
don't need like any t with that.
Well, there's no t, so you can't plug in tau. It's constant.
So is it only if it's like a variable?
Well, if you have the variable, then it's tau, right?
If you say like switch it around, say that's the g part. and
Yes.
You just put t for the different sign, or just tau.
Yes, and when you integrate, it will be cosine tau, and you get the same answer. Because it's convolution, and convolution is commutative, so you can. That will make the problem a little bit easier, right? Because you put the first one you change into tau, the second one t minus tau. No sniffling. Do you want one more problem of this, or move to the last formula? Wanna try to beast through one on your own, real quick? Let's see if I can find something disturbing. Oh, perfect. Here. Then I don't have to put this one on the test. Or do I? Tangent inverse, nothing scary. 3 over s plus 2. So you hit it with the formula. Did I put inverse in the formula? No, I didn't. Wow. There it is. So you immediately apply the formula. Your answer that you're looking for is equal to negative 1 over t, inverse Laplace of, and then you take the derivative of the whatever you see. And you just go from there. Let's see what you get. No pressure, you have 18 seconds. Just come. right? So we are going to use the use the force. The inverse Laplace transform does not contain any of the inverse tangents in there, right? So we write f of t is equal to negative 1 over t times the inverse Laplace of, and now we take the derivative of this. Now to take the derivative in terms of s, it's going to be the of this form 1 plus 3 over s plus 2 everything squared, and then the derivative of 3 over s plus 2 goes on top, and that would be the derivative of this thing now is 3 times s plus 2 squared, so that's 3 over s plus 2 squared, but only denominator is squared. Alright, so now that we have that part, just a little bit more algebra. 1 over t, inverse Laplace of, and now these denominators will cancel completely, right? If I multiply, well, let me write it. So s plus 2 squared, and then times s plus 2 squared. So when you multiply with this, you will get that this is just a 3 on top. Over here you're getting s plus 2 squared, and then over here plus 9. Do we all see that? Are we all good with that? So 1 times s plus 2 squared is s plus 2 squared, and then s plus 2 squared, s plus 2 squared cancels, but 3 squared on top stayed as 9. Now I can't cancel 3 and 9, obviously, because of the, right, there's no 3 there. But isn't this just a shifted sign? Right? This is a shifted sign. So e squared, e to the 2t, I mean, e to the 2t, and then you have a 3, and you have the sign of 3t.
E to the 3t. Oh wait, no, never mind.
No, 2, right?
Yeah.
Because that's plus 2. Actually, it's on the chart. This one is straight on the chart. The whole thing. So if you look at the chart, let's find it. There it is. This one right here. Because you have s plus 2, right? S plus 2 squared, and that's 9, and that's 3. So straight in the chart.
We're getting this chart right.
Yes. So it's e to the negative 2t sine 3t.
So you can memorize the chart at the beginning.
Yes, you get to memorize the chart, and so, right. So this thing is equal to negative 1 over t times e to the negative 2t sine 3t. And that's the inverse transform. There was no other way to do it. No other way to do it. Let's see if I can. I think it's sufficiently funny for a book. Oh, come on. I'll take regular pictures and I'll mess with it later. It looks good. Alright, I'll see. We have enough time.
Where did the T come from?
Which T?
Like before the Laplace, is that just something?
This one?
That's just a formula?
Yeah, that is from the definition of from the formula from theorem right here. That if you are using the inverse Laplace of the original function, you can replace that with the inverse Laplace of the derivative if you multiply it, if you pre-multiply it by -1/t. Now we have one more. And we're done. Yeah, stop breaking that. Integration. So integration of transforms, Laplace transform of f of t divided by t is equal to integral s to infinity of f of sigma. This thing is just a dummy variable, so you might as well put f of u du. So that's the part. But then the part that we actually need and want and love is the inverse Laplace part, which tells us that we can just do the t times the inverse Laplace of the integral s to infinity. So it's a improper integral, and don't let this sigma freak you out, as I said. No. When is it useful? Again, it's useful when again, it's the one that it's on the bottom that we are going to use. So f of t, right? F of t is the inverse Laplace of f of s. But then you can integrate if that f of s is integrable, right? Then you want to consider using this formula. So let's find the integrable case. Here it is, problem 28. So you solve differential equation, and now you have to do this backwards, and it's cubed. Now you're looking at this and you say, whoa, that's just basic u sub, right? Your s squared plus 1 is u, and you have 2s on top, right? You can make it 2s for du. So integration goes like this. Do what?
I thought it was going to be harder than that.
No, I'm sorry for disappointment, but that's it. Now, this is not in your basic charts, and it's a triple repeat, right? On a quadratic for your beloved partial fraction decomposition. It will take a month, right? So, but you have 6 variables, right? At least, right? So Can you do it with convolution? Yes or no, because there will be cosine, sine, and sine. Yes, it's just way too much. So let's do this the proper way. You're looking at this. All other options are not friendly. So your f of t is immediately t times the inverse Laplace of the integral s to infinity for, and now you change all these x to sigma. They like sigma variable here, so tough luck, right? Gotta learn how to write that one. And all you need to do is to integrate that u sub, right? So u equals sigma squared plus 1. du is 2 sigma d sigma. I don't have a 2, so I'll fix that with 1/2 and 2 in the integral. And what we get is t times the inverse Laplace of, now we have the limit, well, let's not forget 1/2. So let's do this. 1/2 limit b goes to infinity, the integral of s to b and now I have my du over u, and this limit changes into s squared plus 1, and the upper limit changes into b squared plus 1, right? Because you use these limits to change that. Nice. So that's equal to t times the Laplace transform of 1/2 limit b goes to infinity, and now that's ln.
Isn't u to the third power?
Oh yes, it is. Thank you. So I lied. It's not ln. It's u cubed. It's -3. It's -2. So it's -1 over 2u squared, right? Is that good? Let's say it's good, right? Just walk away. S squared plus 1, b squared plus 1, times inverse Laplace of 1/2 limit b goes to infinity, and I have -1 over 2 times u squared, so that's gonna be b squared plus 1 squared, minus and minus will give me plus 1 over 2 s squared plus 1 squared equals to t times inverse Laplace of 1/2. This first one goes to 0 because of the limit, and the second one stays as is, so I can just change that to 1/4. So I have 1/4 times 1 over s squared plus 1 squared closed. So this quarter can escape outside, and I have a convolution over here between 1 over s squared plus 1 times 1 over s squared plus 1. See that? That's two signs. So it is 1/4 t times the convolution of sine t and another sine t, which is further equal to 1/4. Now this looks insane, but remember, there's no other way. 0 to t sine tau times sine t minus tau d tau. And what you can do there for the sine t and the one on the bottom is you again have to use the formula from your pre-calc 2, right? The product to sum, so that you can have two separate sines and cosines to deal with. It's a good exam question, right? No, this is something you do on Sunday because you have nothing better to do, you know. Just keep cranking this. You make this into a full page. So I'm just gonna say, okay, now use product to sum formula, and then 3 dots, and in 15 minutes is done.
Okay.
So if you write down the passage is fully correct?
Of course.
Well, you didn't get 7 at the end, so you know what I mean. We put separation of variables. Put a question that clearly says dy over dx is equal to 3x, use Laplace transform. just so you have something to work with. All right, well, that's you've seen them all. Convolution and the derivative and the integral. Now you just go home and like crank these problems, you know, over time. Should be good. All right, let's say bye to the stream. Bye stream.